Hi viewers, in this video we will solve problem 5.11 from the book Applied Thermodynamics, McConkey and Td Eastop. Here is the statement of the problem 5.11. So a 1 kg of fluid at 2.62 bar minus 3 centigrade is compressed according to a law, that is PV is equal to constant, to a pressures of 8.2 bar. Calculate the work input and the heat supplied when the fluid is air. So first we will solve this problem 11 from the chapter 4 for the fluid when the working fluid is air. So the pressure P1, that is 2.62 bar, temperature that is minus 3 centigrade, convert that into Kelvin, so you will get that is 270 Kelvin. Pressure P2 at which it is compressed, that is 8.2 bar. We need to find the work input during this process and the heat that is rejected. We need to calculate. So if I draw its TS diagram for this process, this is the high pressure line, this is the low pressure line. Horizontally, as it is the isothermal compression that follow this law, PV is equal to constant. So the process, in this process compression takes place from process 1 to 2, so it will be obvious that heat is rejection takes place. Heat rejection is there, and also the work is done on the system. So this is follow the process 1 to 2, and the entropy at this stage is S1 and entropy at this point is S2. Okay, so during this constant temperature process, the temperature is 270 Kelvin. The work that is required that is done on the system is equal to RT ln P2 divided by P1. So what is R? That is constant for the air, 0.287 multiplied by the temperature, that is 270, multiplied by ln P2, higher pressure, that is 8.2, and the lower pressure, that is 2.62. So after simplifications you will find its value, that is 88.413 kilojoule per kg. Remember, this work is done on the system. Next we need to find the heat that is rejected during this process. So the heat, according to first law of thermodynamics, when it is supplied, equal to the sum of the work plus change in internal energy. But during this process, change in internal energy is 0. So the heat that is rejected in this process is equal to the work done that is done on the system, that is 88.413 kilojoule. So during this compression process, heat rejection takes place, but in thermodynamics rules, when you represent the heat rejections, you will represent it from negative sign. So here we can say W, in front of W we can write the negative sign. So the heat that is rejected is 88.413 kilojoule per kg. So these are our final answer for the working fluid when it is air, and that is the work that is done on the system and the heat that is rejected from the system. I hope you understand it. And next, now we will find the when there is a refrigerant initially dry saturated, 2 bar, and pressure P2, that is 8.2 bar, temperature T1, that is minus 3 centigrade, and temperature T2, that is 32.3 centigrade. So compression takes place, but this time the working fluid is refrigerant that is initially dry saturated with properties given in the table 4.2. So the tables that is provided, I already shown it on the screen, so you can clearly understand where I am picking the values of from this saturation values. So first let me draw its trace diagram. Remember, when there is a refrigerants initially dry saturated, it means there is a dome shape exists. This is the high pressure line, this is the low pressure line. The pressure, this is the pressure P2, this is the pressure P1. As it is clearly mentioned that when the fluid is refrigerant initially dry saturated, so it means that our state point 1 lie at this point, the saturated region. So it is dry saturated at the pressure P1. So after that, compression takes place, and it reached to the pressure P2 from process 1 to 2. During this compression, its entropy change. So the entropy at this is S1, and entropy at this point is S2. From the temperature T1 and the pressure P1, the specific volume is state point 1 is 0.0757 meter cube per kg. And next we need to find its internal energy, that is equal to H1 minus P1 V1. So what is H1? That is nothing but Hg1 minus P1 V1. And where you will get this Hg1 value? This is the Hg1 value at state point 1, that is 292.93 minus pressure P1, that is 2.62 multiplied by 10 to the power 5, because bar, to convert bar into Pascal, multiplied with 10 to the power 5. Next is the volume, that is 0.0757. Now multiply means divide this whole term with 1000 to convert that into Kelvin, because in kilojoule, sorry, because this term is also in kilojoules. To convert this term in kilojoule, you must divide this with 1000. So after simplifications, we will find the internal energy, that is U1 is equal to 273.11 kilojoule per kg. Now come to the state point 2, pressure P2 and temperature T2. You can see that the specific volume Vg2, that is 0.0248 meter cube per kg. Now this is the saturated volume at state point 2. That is not our exact volume at state point 2. For that we need to find it using the formula P1 V1 is equal to P2 V2. So this V2 will be equal to P1 V1 divided by P2. Sorry. So now the V2 is equal to, that is P1 value, that is 2.62 multiplied by V1, that is 0.0757 divided by P2, that is 8.2. After simplifications, you will get the V2 value, that is equal to 0.0242 meter cube per kg. if you compare this V2 value, that is our state point 2 value, and with this saturated specific volume value, so you can conclude that this V2 is less than VG2 value. So it means that VG2 is the value at this point, and V2 is the value of state point that must be lie beyond this line. So it lie here. We mentioned that it lie here. Okay, so it means that our state point 2 is in the wet region. So this is our conclusions point, so where our state point will lie. That's why we find this from the steam table and this from our formula that is given in the statement. So now to find the dryness fraction, this x2 will be equal to V2 divided by VG2. So what is V2? V2 is 0.0242 divided by 0.0248. Upon simplifications, you will get its value, the x2, that is equal to 0.975. The next we need to find the internal energy and enthalpy also for finding the internal energy. So enthalpy for the state point 2 is equal to HF2 plus XHG2 minus HF2. So where you will find these value? That is very simple. This is HF1 value, sorry, HF, these are HF2 value, and this is HG2 value. Now put these value in the equations, in this equation, to find the enthalpy for the state point 2. So what was the HF2? That is 144.29 plus dryness fraction 0.975 into what is Hg2 value, that is 1313 minus 154.29. So after simplifications you will get the enthalpy value, that is 308.8 kilojoule per kg. Now the enthalpy at state point 2 is equal to H2 minus P2 V2. So what is H2? That is 308.8 minus pressure P2, that is 8.62 bar into pascals, multiply with volume, that is V2 0.0242. To convert this whole terms into kilojoule, convert that, multiply with 10 to the power minus 3, and you will get the final internal energy U2, that is 289.05 kilojoule per kg. During compressions, work is done on the system, so the work is done on the system, that is equal to P1 V1 ln P2 divided by P1. So what is P1? That is 2.62 multiplied by a volume, that is 0.0757 ln, what is ln P2? P2 is 8.6 divided by 2.62. After simplifications you will get the work that is done on the system is equal to 22.63 kilojoule per kg. Next, from the first law of thermodynamics, the heat that is supplied is converted into work done plus change in internal energy. So this work is done on the system, that's why we take its value negative. So the heat that is rejected in this case is the heat that is supplied is 22.63 plus change in internal energy, that is U2 minus U1. Put it value. What is U2? That is 289.05 minus 273.11. After simplifications, you will get the heat value, that is minus 6.69 kilojoule per kg. This negative sign shows that rejection is takes place during this process, and the refrigerant is initially dry saturated and it is compressed to the pressure E2, that is 8.6 bar. I hope you understand it. If you still confusion, you can ask. Subscribe my channels if you haven't subscribed yet. Thank you.